Hi everybody, Physics Ninja here. Today what we're going to do is we're going to work on a giant problem set dealing with momentum, conservation of momentum, and collision problems. I've put together this giant review problem set. I have 18 problems. There are 45 questions. The questions deal with all kinds of topics relating to 1D collision, 2D collisions. We're going to look at elastic collisions, inelastic collisions, cannonballs firing, objects exploding, anything you can think of, problems with springs, masses hitting springs, springs connected to the masses that are colliding with each other, blocks hitting other blocks, every kind of problem you can think of here. We've got 18 problems, 45 questions. All right, what we're going to do now is what you need to do is you start by downloading the problem set. I will post the link in the description of this video. What you do is you go through the problems, try them out for yourself. Then you come back and watch the video and check your answers. You cannot simply watch the video and expect to learn anything. Physics is not a spectator sport. You need to try them out for yourself. All right, if you like this video, give it a thumbs up. Consider subscribing to Physics Ninja. It is the best way to support what I do. All right, let's get started. All right, here's our first problem here. We have two balls of equal mass are thrown horizontally with the same initial velocity. They hit identical stationary boxes resting on a frictionless horizontal surface. The ball hitting box 1 bounces back, while the ball hitting box 2 gets stuck on the box. You can assume that there's no motion in the vertical direction before or after the collision. All right, so the first question says, which box has a greater speed after the collision? All right, is it going to be the one where the ball bounces off or if it sticks to it? Okay, so the key to this problem right here is to note that for the system composed of the ball and the box, there is no change of momentum. So it means if you consider the change of momentum of the ball, for example, plus the change of momentum of the box, this must be zero. There is no change of linear momentum during this type of collision because there's no external forces. So all you do now is you bring the box on the other side. And if I bring the box on the other side, I'm going to have the change of momentum. Let's rewrite this. The change of momentum of the box, or let's just bring the ball on the other side. The change of momentum of the ball. Okay, so we have to look at this term. In which case is the change of momentum of the ball the biggest? Clearly in this one, it has momentum going this way, then it has momentum going in the opposite direction. So the change of momentum of the ball is going to be bigger in the case where the ball bounces. Okay, so if that change of momentum is the biggest for that term, it means that there's going to be a bigger change of momentum for the box. Okay, this is really one of the keys to this problem. It's very, very important to understand this. In this case, when it sticks to it, everything is going to be moving to the right after the collision. Its change of momentum, if I'm only looking at the ball, is going to be smaller. Therefore, the change of momentum of the box will also be smaller. All right, next question says, so the mass of the box is 1.7 kg and the mass of the ball is 0.4 kg. Suppose the ball has a horizontal initial velocity of 13 meters per second. What is the speed of the box 2 after the collision? All right, so we're looking at scenario 2 where it sticks to it. So this is an elastic collision. If you use momentum conservation, this is what it looks like. Before the collision, all you have is the ball moving with some velocity. And after, what do we have? Everything sticks together, so the total mass of the system is m1 plus m2, and everything, the ball and the box, are moving together. All you have to do now is we need to solve what is this v final. So I'm just going to rearrange this equation. m1 v1 is the momentum of the ball before the collision. I divide through by the total mass of the system, and now you substitute the numbers. We get 0.4 for here. It was moving at a velocity of 13, and here I do 0.4 plus 1.7. All right, we put that together. We get that the final velocity, again, of the box and the ball moving together is 2.5 meters per second. I'll go ahead and box that up. Now we look at our choices. That choice corresponds to choice D is the correct answer. All right, let's go to the next problem. Problem 2 says mass m1 initially has a velocity of v0 in the positive x direction along a frictionless horizontal floor. It collides with this block over here, m2. Immediately after the collision, m1 is moving in the negative x direction with a speed of v0 over 4, and m2 is moving in the positive x direction with a speed v0 over 2. First question says, is this collision elastic? And there's a hint over here. It says almost no math is needed to answer this question. All right, so how do you check if it's an elastic collision? This is very, very important, especially for 1D problems. Now you could write something like this. M1 half, what's the kinetic energy of that initial block? The M2 initially has no kinetic energy, so if it's an elastic collision, energy should be conserved. You should do something like this, V naught over 4, but you got to square this entire thing, and plus 1/2 M2 V naught over 2 squared. All right, now you could check all that out, but they don't really give you the masses, so you'd kind of be stuck if you did this. But one thing to remember, and one of the key points to this is, if it's elastic, what you check is you look at the relative velocity before the collision. Let me just write that down. Must be equal to the relative velocity after. Now again, we're just going to look at the magnitude here. It really is a negative sign in front of it. Relative velocities after. This is what it looks like in a collision. You do V1 initial minus V2 initial, and this is our equation. It's V2, sorry, that should be V1 final minus V2 final. All right, this is our equation. So relative velocity before, that is that. And I'll put a negative sign here just to indicate the relative velocity after, so it's consistent with this equation. It doesn't look identical to this, but this is a true statement over here, that if it's an elastic collision, it satisfies this equation. So now we substitute our values over here. So what do we have for V1? We have that the velocity is V0, so we check that out. So here I would do V0 minus 0 for the M2 initial. So we're done with that side, and now we go over here, and V1 final. V1 final is V0 divided by 4. However, it is moving in which direction? It's moving in the left direction. So here I would have to do V0 over 4, and then minus the final velocity of object 2. This is V0 over 2. Anyway, you could see right away that these two terms are not equal. So that means that this collision is not an elastic collision. So this here is a really, really quick way to check whether or not 1D collisions are elastic or not. All right, let's go to the next one. Which of these following expressions expresses the relationship between the two masses? So we can't use conservation of kinetic energy. What we have to do now is use conservation of linear momentum. So let's write it out for this problem. Before, the total linear momentum is just the momentum of block M1, and that's its value. After the collision, what do you have? You're going to have M1, and it's moving to the left. Therefore, its velocity is V0 over 4. I have the negative sign there to indicate its direction. Plus, the block M2 is moving to the right. It has a velocity of V0 divided by 2. All right, now careful here. They're asking us basically what M2 is. That is our variable right here. What we have to do now is simply do some algebra in order to isolate and substitute. So one thing we could do is you could cancel out all of the V0 terms. They appear in all of the terms. Next, we're going to bring this term onto the other side just to group all the M1 terms, and then we do a little bit more algebra. We'll get to a value for M2. So when you bring this on the other side, what you're going to end up getting here is 5/4 M1, and that there must be equal to M2 divided by 2. Bring the 2 on the other side. You're going to get that the mass M2 is equal to 5/2 M1. Okay, so that there corresponds to choice B as being the correct answer. All right, let's look at the next problem now. Mass M2 continues to the right and slides up a frictionless ramp. It momentarily comes to rest at the maximum height over here, shown in this bottom figure. Which of the expressions gives you the maximum height reached by M2 in terms of that initial velocity? All right, so from the point forward where this block here starts moving all the way till it gets to its maximum position, we do have conservation of mechanical energy now. So initially all we have here is some kinetic energy here of block number 2. And at the end, all you're going to have is some gravitational potential energy of block number 2. So you simply have to set those expressions equal to each other. So this is what it looks like. Our kinetic energy right after the collision is this. It's m2. And it's moving with a velocity of v0 over 2 squared. That there must be equal to the final gravitational potential energy here for block M2. So what you do here, this is simply M2 G times H. Now we want to solve for H, so you can cancel out the M2s. They're on both sides of the equation. You divide through by little g, and we get an expression for H, which equals to v0 squared over g. Now careful here, you're going to have to square this term over here. You're going to factor a 4 that multiplies 2. You should have an 8 here in the denominator. All right, so we look at all our choices. That looks like choice E to me. And we are done this problem. Okay, a lot of important concepts in this problem. Here's problem 3. It says a bomb initially at rest at the origin explodes into 3 fragments that move in the XY plane. The left fragment here has a mass 24 kilograms and moves in the negative x direction with a speed v1. The fragment that move to the right have the same mass m2, so we got 2 chunks here that have a mass m2, and they move with the same speed. One is moving at an angle of 25 degrees with respect to above the x-axis, and the other is moving, again, at 25 degrees below the x-axis. Which of the following statements correctly compares the situation before and after the explosion? So let's have a look at these. So this one says momentum is conserved in the x and y direction. Kinetic energy is not conserved. Okay. Choice B says neither momentum nor kinetic energy is conserved. And the last one says momentum's conserved in both of those directions. Kinetic energy is also conserved. Well, let's think about what we have before. Before we have a big chunk of stuff and nothing is moving. So clearly the kinetic energy before has to be 0. The initial momentum here must also be 0 in both directions. What do we have after? After, clearly you can see that all of these chunks are going to have some kinetic energy, right? The final kinetic energy is clearly not equal to 0 because everything is moving. So right away, you can already see that kinetic energy is not conserved. Okay, so we can get rid of, choice C right now because it says that that is conserved. Okay, so what about momentum? Is momentum conserved in this type of explosion? As long as there is no external force, momentum will be conserved in all directions. This bomb going off is internal to the 3 chunks right here. So if there's nothing external, we're going to have momentum is conserved. Okay, so really the correct choice for this one here has to be choice A. It's conserved in both x and y directions, so this is like a 2D collision problem. Okay, we can get rid of choice B over here. All right, the next problem says if the ratio of the speeds v1 divided by v2, this is after the collision, what is the mass of each of the 2 rightmost fragments m2? Okay, so we want to determine what this guy is. We know the mass of m1 here is 24 kg. So the way that you would solve this problem is I would write a momentum conservation equation for the x direction, and I would do the same thing for the y direction. And then let's see how we could solve both of these equations. So before the collision, it's very easy to write both statements. We have nothing moving, therefore there's no momentum in that x direction nor the y direction. After the collision, what do we have? We've got the block M1, this big chunk, and it's moving to the left at some speed v1. Okay, so I'm going to write minus v1. Minus just tells me the direction of that motion. And v1 is the magnitude, okay? It'll be that speed after the collision. What else do we have? Now we've got 2 chunks here, and they are moving at different angles here with respect to the horizontal. So what we need to do is you need to break that velocity down, and you need to write it as an x component and a vertical component. You do that for each one. So this is what it looks like. Now, clearly, if the angles are the same, the speeds are the same, the masses are the same, what you're going to end up having here is both of them are going to have the same momentum here in the x direction. And that velocity here in the x direction, this term over here, should be v2 cosine of theta. So this you should be able to do some trigonometry and show you that this here is in fact the x component of mass 2. So that's it for this equation right here. What else? We really have everything we need. We can write down the vertical equation, but let's go see what we get for that vertical equation. Vertical equation, we get m1 doesn't have any final momentum in that vertical direction. And what you're going to have here is equal and opposite momentum here for m2s in that direction. So this really doesn't lead us to anything, right? It basically leads us to 0 equals to 0. There is no final momentum before and after the collision. So we're going to focus really on our first problem right here, our first equation. And all you have to do now is, knowing the fact that we know this ratio, we can solve for the masses. So what I'm going to do with this equation here is I'm going to divide through by V2. And if I do that, in this second term over here, I get to cancel those out. Now this ratio I know is 2.5, so I'll be able to substitute that into my expression. What you're solving for here is m2. So let's do a little bit of algebra just to get this by itself. Give myself a little bit more space. I bring the first term here to the other side of the equation. You get what? You're going to get positive m1 v1 over v2, the ratio that they gave us. That there must be equal to 2 m2 cosine of the angle theta. At the end, I get m2 equals to m1 v1 over v2, and I bring the 2 cosine of theta over to the other side. Now I'm in a position just to substitute in all the numbers. The mass m1 was 24 kilograms. That ratio is 2.5. And then I do 2 cosine of my angle was 25 degrees. That's it. You plug in all those numbers into the calculator. You should get a mass m2, which is equal to 33.1 kilograms. 33.1 kilograms corresponds to choice B. All right, that's it for this problem. Let's go to problem 4 now. All right, problem 4 says 2 cars collide in an icy intersection. The mass of car 1 is 440 kilograms. The mass of car 2 is 560. Car 1 was initially traveling east at 12 meters per second, while car 2 was initially traveling north at 17 meters per second. After they collide, they stick together and slide off at an angle theta with respect north of east as shown over here, as shown in the diagram. First question says, what is the kinetic energy of the cars as they slide together immediately after the collision? All right, so how do we determine the kinetic energy after the collision? Well, kinetic energy has to be, the final here is 1/2. We're going to have both objects moving, m1 plus m2. And guess what? Well, they're going to be moving at some final speed. All right, I'm going to give you a little tip over here that when you're dealing with momentum problems, collision problems, it's often useful to write the final kinetic energy in terms of the momentum. All right, and we know that the momentum is the total mass times the final speed. So you can write this here as the final momentum of that system divided by that total mass. Now the reason that this is particularly useful is we know that the momentum must be a conserved quantity. Therefore, the P final here has to be equal to the P initial. So if you can find P initial, and we have all the information we have to find the initial momentum, you can easily find what P final is. They have to have the same magnitude. So this is very, very important, is that the magnitude of P initial must be equal to the magnitude of P final. All right, so how do we do this? Well, let's look at what is the initial momentum here in the x direction. What is the initial momentum here in the y direction? In the x direction, all you have is m1 v1, right? Mass 2 is just moving north, so that's it. Now we substitute the numbers for this one. I put 440 multiplied by 12. I get 5280 kilograms meters per second. The initial momentum here of car number 2, again, it's its mass times its velocity. Again, that is only in that vertical direction over here. So what do you get? Put the numbers in, 560, this time multiplied by 17. We get an initial momentum here of 5920 kilograms meters per second. So now I can find what is the magnitude of this total initial momentum, right? Because we know both components. So all you have to use here is Pythagorean. We have the initial momentum in the y direction and in the x direction. You put in all their numbers, and what you're going to find here, squaring those and then summing, taking the square root, you get 10,886. That is the magnitude of that vector, that initial momentum vector before the collision. All right, so this must be equal to the final momentum after the collision. So all we go back now is to our kinetic energy equation, and you can go ahead and substitute. That final momentum must be 10,886. I have to square that value, and here I divide by that total mass. This here is 440 plus 560. We put all those numbers in the calculator, you'll get 59,200 joules of final kinetic energy. So that there is basically choice E right here. All right, what about question 18? It says, suppose the answer to the previous problem is K. If the initial speed of each car was doubled, how would the new kinetic energy of the cars sliding together immediately after the collision compare? Well, what happens here if I would double the speed of each car? I would basically double each component over here, right? I basically have times 2 and times 2. That would basically lead to twice the initial momentum, and it would also be equal to twice the final momentum. So guess what? If I put an extra 2 factor in here, but I have to square that term, I'm going to get 4 times the kinetic energy that I had in the previous case. So in this case, we're just using that factor, but you can't forget to square it. So that is really the key point over here. So I should have 4 times as much kinetic energy if I double the speed of each object. All right, so what about the next problem? If the initial speed of each car was doubled, how would the angle they slide at after the collision compare to the original problem? Again, now for this one, we have to use some reasoning. If I double that velocity, what am I doing? I'm making this vector bigger. I'm making that vector bigger, but I'm making it bigger by the exact same amount, by the same factor. I'm not making one doubling and the other one, staying the same. They're both doubling. Therefore, what does that mean? That means this final momentum is also going to double, but it's not going to change the direction. All right, so this is really, really important. So in this case, the angle would stay the same. So make sure we understand this problem. This is also a good one that we have to reason just by looking at all our vectors. All right, here's problem 5. 2 carts move toward each other on a one-dimensional horizontal frictionless track. Cart 1 has a mass of 21 kilograms, an initial velocity of 12.143 meters per second. Cart 2 has a mass of 32 kilograms, and its initial velocity is minus 0.469. A spring between them makes this collision between the carts elastic. So that's going to be an important point. First question says, before the collision, what is the velocity of cart 1 as viewed by someone in the center of mass frame? All right, so this is a different style of question. Well, as viewed by in the center of mass frame, how would we write this as an expression? What we're looking for here is the velocity of 1 relative to the center of mass, not relative to the ground. Okay? This here should be the velocity of object 1 minus the velocity of the center of mass. So what we have to do here is we know the initial velocity here. This is 12.143. What we don't know is the velocity of the center of mass. So this is what we first need to calculate. So how would you write the velocity of the center of mass? Well, for that, we have to use our expression. We do this, 1 divided by the total mass. This is m1 plus m2. And again, now we have to sum the masses and their velocities. Okay, so in this, we know all the information here. So we have the total mass, m1 plus m2. And this term over here becomes m1 v1 initial plus m2 v2 initial. Now we do have to take direction into consideration when you're substituting these velocities, so be a little bit careful with that. But we're ready to substitute in our numbers to find the velocity of the center of mass. So the total mass for this problem is 21 plus 32, okay? Now the term here in the bracket is m1, 21. Its initial velocity is 12.143. And now we do plus the mass of M2 is 32, and its velocity here, they also explicitly told us it was negative, so 0.469. All right, you put all those numbers in the calculator, and you get that the velocity of the center of mass is 4.53 meters per second. Now we have to be careful. That is one of our choices, but that is not what they're asking for. They're asking you for this term right here. So the velocity of 1 relative to the center of mass will be the velocity of 1, 12.143, and then minus this velocity of the center of mass, 4.53. Put that in the calculator and you get 7.61 meters per second. All right, so this is really our final answer, and that is what the question is asking for. That is choice E right here. All right, after the collision, what is the speed of cart 1 as viewed by someone in the reference frame of car 2? All right, the easiest way to answer this problem here is to note that this is an elastic collision. So what does it mean? It means that V1 initial minus V2 initial must be equal to minus V1 final minus V2 final. That means the relative velocity before the collision, which we can calculate because we know all our numbers, it must be equal to the relative velocity after the collision. Now, they're asking you for the speed of cart 1 relative to cart 2, so what we're really interested in is just the magnitude of this term. So what we could do here is just put magnitudes and forget about that negative sign. But this is what you're looking for, but you can use all of the initial information in order to solve this. So it's much easier to use the left-hand side to calculate all of this than setting up two equations and two unknowns and doing a bunch of algebra. All right, so this is what we do. So the initial velocity of cart 1 is 12.143. The initial velocity of cart 2 was minus 0.469. Put that in the calculator. Again, I'm going to get 12.61 meters per second. That'll be the relative velocity or the relative speed of cart 1 relative to cart 2 after the collision. Okay, so that looks like choice E to me. That is the correct answer. All right, let's go to the next problem. Here's problem 6. A cannon of mass of 2,100 kilograms is initially at rest on a horizontal frictionless surface of ice. It fires a cannonball that has a small mass of 55 kilograms. An observer on the ice measures that initial angle to be 25 degrees above the horizontal, and its initial velocity is 290 meters per second. The cannon recoils and slides to the left over here. All right, the first problem says, considering the system made up of the cannon and cannonball, which of the following quantities are the same just before and just after the cannonball is fired? Choice A says both the horizontal and vertical components of momentum. The horizontal components of momentum for choice B, and choice C says the vertical component of momentum. So which component of momentum is conserved over here? Let's think about this. This is X and Y. And the key is that momentum is a conserved quantity, okay? When is it a conserved quantity? It's not always conserved. It is conserved when? If no external forces. So you can have an explosion here that fires this cannonball, and that is fine. That is internal to the cannon and the cannonball. Now, the other forces that are going to be at play over here are, guess what? You're going to have the weight. You're also going to have a normal force. And while that is getting fired, this normal force is going to get bigger, okay? So this is going to be an external force on the system here, which means that the momentum in the vertical direction will not be a conserved quantity. That means also, clearly, both components are not going to be conserved. So only the horizontal component is going to be conserved here. That's all we have. All right, in the reference frame of the cannon, the initial angle of the cannonball relative to the surface is what? Is it going to be bigger than 25 degrees, less than 25 degrees, or equal to 25 degrees? So imagine here you have the cannon that is recoiling back. Right? If you're sitting on that cannon, what do you see? You see that that ball here is going to have a bigger velocity here in that X component. You're still going to measure the same vertical component here, but clearly the velocity of the ball as seen by the cannon is going to be bigger than for someone who's looking at it from the ground. So that's going to make that component here only in the x direction a little bit bigger. And at the end, that's going to tend to make this angle here that's going to look smaller than 25 degrees. So that's a little bit of a tricky problem. All right, here's the next question. At the instant the cannonball hits the ice, how far to the left of its initial position has the cannon moved? Okay, so this is what we have. We have our cannon here, which is undergoing now some projectile motion. It's going to travel a certain range. That range I could calculate. For that, you simply have to go back and revisit our kinematics. Sine of 2 theta divided by little g. We substitute in all our numbers. We know this initial speed here is 290. We know the mass is 55 and so forth. Little g is 9.8. Actually, you don't need the mass, but we do need that initial angle of 25 degrees. And you should get something like this, 6574 meters. So that's the range of this cannonball. But how far has, clearly the cannon's not going to move back this far because it has more mass. So one principle we could apply for this, we could apply to this problem is to note that the position of the center of mass before and after this firing, it cannot change. So its displacement must be 0. So how do we do that? Well, how do we find the displacement of a center of mass? We do the divide by the total mass, and now we evaluate this. We add up each one and multiply by its displacement. Okay, so let's go ahead. Now, I don't really need to worry about this term of the total mass because I have 0 here on the left-hand side. So really, I only have to evaluate this summation. So what I'm left with here is the mass of the ball multiplied by its range plus the mass of the cannon multiplied by its displacement. So this is it. I simply have to solve for this. I know all of the masses. So the cannon here is going to recoil a distance of minus the mass of the ball divided by the mass of the cannon and multiplied by that range. We go ahead and we substitute. Notice the negative sign, that simply means that the cannon is going to recoil to the left. 55 over, what do we have? 2100 for the mass of the cannon, and I just calculated that range as 6574. I put everything in the calculator and I should get that the displacement of the cannon here is approximately 172 meters to the left. And that there corresponds to choice C. Now they just have all positive answers. That's because they're simply asking you for, oh, they're already telling me it moves to the left, but they just want to know how far it moves. So there's no positives or negatives in any of those choices. They're all positive. All right, that's it for this problem. Kind of a good problem. Let's go to problem 7 now. All right, here's problem 7. We have a box of mass m1 slides on a horizontal frictionless surface with a speed v1. It collides with and sticks to an initially stationary box of mass m2. All right, the speed of the boxes moved together after the collision is v2. Okay, which of the following expressions is a correct expression for m1 in terms of the other variables? So for this, we're going to use conservation of momentum. So we have what? M1, we have v1 equals to, again, everything sticks together. So it's m1 plus m2, the total mass, and everything here is moving with a speed v2. Now what they want is m1 in terms of those other ones. So we have to group together all the m1 terms. So we got to do a little bit of algebra. So if I group together all the m1 terms, I have v1 over here, and I have to bring this term over here onto the other side, onto the left-hand side. So this will become minus v2, and this will become m2 v2. So now we simply divide through by v1 minus v2. So you should get that my final expression for m1 is m2 v2 divided by v1 minus v2. Okay, so let's just box that up. That there looks like, which choice do we have? That looks like choice number C to me. All right, now they're giving us the masses M1 and M2. What is the ratio of the final kinetic energy of the blocks just after the collision if the initial kinetic energy of the blocks just before the collision is Ki? Okay, so the way that I would set this up, well, let's just start by solving what is the initial kinetic energy of my system. It's only the block M1 that's moving, so that's easy. It's M1, and it's moving at a speed V1, and you got to square that. That's the initial kinetic energy. The final kinetic energy of our system now, Well, you would write this is K final. It's 1/2. The total mass now is m1 plus m2. And everything here is moving at some v2, some final speed, right? Okay, so how do you find the final speed, first of all? For that, you can use this momentum conservation expression that we had in the previous case, right? You actually have an expression for the final speed because it's m1 v1 divided by the total mass of our system. All right, so what you need to do is you need to substitute this v2 into this expression. All right, so you get m1 plus m2, and then we're going to square this whole thing, and v2 is m1 v1 divided by that total mass. All right, let's just evaluate this square here. You end up getting 1/2. If I square this, you're going to get, this is m1 squared, v1 squared, and this will end up dividing through by what? By this total mass here. You're going to have m1 plus m2. All right, now go back to the question. They're actually asking you for the ratio of both of those. So you have to be careful with the algebra. This is what they want you to evaluate. So my final kinetic energy, I'm not going to put the 1/2 factors. They're going to cancel out with each other. But all the other terms, let's include them. So you get m1 squared. Here you get v1 squared. And this is the total mass, m1 plus m2. Okay, that's K final. Now I need to divide through by K initial. Again, leaving out the 1/2 terms. m1 and what else? v1 squared. Okay, so you can see that the v1 squared terms cancel out. One of these m1 terms cancel out. And now we're simply left with m1 divided by m1 plus m2. I think we're in a position now to substitute those values because m1 is simply 2, and here you have 2 plus 5. So we're going to get that this ratio here is 2/7. All right, so that there corresponds to choice E. A little bit of work for that one. All right, the last problem now says the boxes now slide into the free end of a spring whose other end is fixed as shown. So it's fixed to a wall over there. If the spring constant is K, which of the following is a correct expression for the maximum compression of the spring in terms of these other variables? So if I'm going to compress that spring, I know that once it's at its maximum compression, the final velocity here of our system has to be 0. There's no more kinetic energy. All of that energy that you had of these blocks moving gets converted into spring potential energy. So we have that our kinetic energy just after the collision, we call that K final here in the previous problem, that has to be equal to that final spring potential energy. So again, our kinetic energy, what did we have? We had 1/2. The total mass, m1 plus m2. And this was v2, final squared. Now this gets converted into spring potential energy. It's 1/2 K multiplied by that displacement squared. Again, the 1/2 factors are going to cancel out. What you want to do here is simply isolate and solve for that displacement of the spring or that compression of the spring. So delta x, then you could see right away, you just have to bring the spring constant down at the bottom. You're going to get m1 plus m2 multiplied by v2 squared. Put a bracket over here, and then divide by that spring constant. All right, now once you take the square root of everything, you'll get to our final expression. If I take the square root of a squared for that v2 term, you can see we're going to take one of those outside of the square root term, and that really looks like your choice C to me. All right, so this is also an important concept that after this collision, we do have conservation of energy because the ground is frictionless here, okay? Therefore, we lost some kinetic energy in that collision, but right after, from this point forward, all the way to the maximum compression, energy is conserved, which allows us to write this statement. All right, here's problem 8. Two cars collide at an intersection. Just before the collision, car 1 is moving from north to south with a speed of 21 meters per second. Car 2 is moving east to west with a constant speed of 35. After the cars collide, they stick together and slide in a straight line a distance d before they come to a stop. Let me just highlight this. All right, the figure schematically shows the place of the collision, and the places where the two cars eventually stop is marked over here with an O. The cars leave a mark on the pavement that makes an angle of 35 degrees below the west direction as shown. The coefficient of kinetic friction between the road and the sliding wreckage is mu k. All right, the first problem says if car 1 has a mass of 800 kg, what is the mass of car number 2? All right, so how do we solve this? Again, this is a 2D collision problem. What you can do is you can write conservation of momentum in our x direction and in our y direction. Before and after, they should be conserved quantities. All right, so in the x direction, what you have is m2 moving here with a speed v2 moving to the left. I'm going to consider that to be the negative direction. So before here in the x direction, I should have minus m2 v2 equals. Now you can see after this wreckage here also has a negative component, right? So we have minus, the total mass is m1 plus m2, and everything here is going to be moving at some final speed. So it's going to be some final speed, but I only want to grab the x component to that, so I'm going to use cosine of that angle theta. I'll call this my first equation. Now in the horizontal direction, the vertical direction here, I'm going to have a similar expression, except now before the collision, I have car M1 that's moving south, so that's a negative value for me. All right, and this is what we have. And then after the collision, you have minus M1 plus M2. What is the vertical component here of this final velocity here? I need to go VF sine of that angle theta. That is equation 2. Now they have given me the angle, which is kind of nice. Now I don't know what M2 is, so you have to do a little bit of work in order to solve for this. What I'm first going to do is, if I can divide through by, or get rid of V final, for example, right? And I can get rid of V final, for example, by taking equation 2 and divide it by equation 1. If I do that, this is what I'm going to have. M1 V1 divided by M2 V2. Okay, now what am I going to have on the right-hand side? The total masses and those negative signs are going to cancel out. Notice that the VFs are also going to cancel out, and here I'm going to have sine theta divided by cosine of theta. Well, that's kind of useful because that's simply tangent of that angle theta. So at the end, here I have one final expression. My goal was to solve what is this mass M2. It appears right here. So we have to do a little bit of algebra, just get it by itself here. So I should have M1 V1 divided by V2 tangent of that angle theta. I know all of these quantities. We just have to substitute the numbers. The mass M1 is provided right here. It's 800. Its speed here was 21. Divided by V2. V2 was 35. And now tangent of my 35 degrees. All right, if I put that in a calculator, I should get that the mass of M2 is 686 kilograms. Let's go ahead and box that up. All right, and that there corresponds to choice E is the correct answer for this problem. All right, which of the following expressions is correct? All right, now look what we have over here. We have all of these combinations here of that coefficient of kinetic friction, the total mass, GD. This here, just by inspection, you should see, first of all, it's all the same for all of these three choices. So this here doesn't help you. This here looks like a force of friction multiplied by a distance. Okay? This here is really what is the magnitude of the work done by the force of friction when it's sliding. Okay? Because once after the collision, it's simply going to slide and come to a rest. So that the final here, let me write final, everything stops. So it's initial after it's going to be equal to 0, its final kinetic energy. Because we've lost some energy due to the work done by friction when it slides. Now look what all of these choices are here. These choices look like the kinetic energy kind of before the collision. Okay? This here's the total kinetic energy before. Well, what do we know? We know that if we have an inelastic collision here where they stick, guess what? We know that kinetic energy is not conserved, right? So the initial kinetic energy before is going to be bigger than the final kinetic energy just after the collision, right? So this guy here is after the collision. Once it starts sliding, now friction plays a role in it, and now you're going to lose all of that energy. But we know that this total kinetic energy before the collision here has to be bigger, okay, than the work done by friction, because I've lost some of that energy right here. Because this term here, the work done by friction, is mu k m1 plus m2 GD is actually equal to the final kinetic energy of this wreckage right after the collision. But we know that this number here is less than that initial kinetic energy because we have a perfectly inelastic collision. All right, so this is a little bit of a more difficult problem, but it's just being able to identify what these different terms are. Here's problem 9. It says a box of mass m slides on a straight frictionless horizontal track with an initial speed v0. It collides with and bounces off a box of mass m, which is initially at rest. After the collision, the box having mass little m is moving to the left with a speed v0 over 3, and the box having mass big M is moving to the right with the same speed, right? Just a different velocity. How are the masses of the two boxes big M and little m related to each other? All right, so for this one here, we are going to have to use conservation of linear momentum. Before the collision, this is what you have, little m moving at some velocity v0. After the collision, you have little m, which is moving to the left. So I'm going to put minus v0 over 3 like this. Plus, you have the box, which is big M, and it's moving with v0 over 3 on the other side. Okay, now, just simply, we only have one equation. We can cancel out all of the common terms. Those are the v0 terms. And all we want to do is write big M in terms of little m. So let's just bring this term here onto the other side. That'll become a positive 1/3. So you're going to be left with 4/3 little m is going to be equal to big M divided by 3. I can see right away you could cancel out those 3's, and you're left with our final expression, where big M is 4 times the little mass. That's choice B. Which of the following statements is true? We need to know the masses of the boxes in order to determine whether the collision, whether or not the collision is elastic. The collision is elastic, and this can be determined without knowing the masses of the box. The collision is inelastic, and this can be determined without knowing the masses of the box. So this we've looked at a previous problem right here. This thing is true because all we have to do to know whether or not it's elastic for a 1D collision is you look at the relative velocities before and after the collision. This would be v2 initial, for example, minus v1 initial must be equal to minus v2 final minus v1 final. All right, so you look at this before the collision, clearly it's not going to be the same because the relative velocity before is v0 or minus v0, and clearly after it's not going to be the same. You don't need to know the masses of the boxes, which is kind of cool, which is kind of interesting. All right, so choice C is the best answer for this one. This applies for all 1D collisions, elastic collisions. All right, that's it for problem 9. Let's go to the next one. Problem 10 says a cart of mass m1 equals to 2 kilograms is moving along a straight horizontal frictionless track with a constant velocity of 3.1 meters per second relative to the track when it hits a second cart that's initially at rest on the same track. The mass of the second cart is m2, which is 3 kilograms. The positive direction is to the right. If the collision is elastic, what is the final velocity of cart 2 in the reference frame of the track? So they want to know v2 final. Well, guess what I'm going to do now? We're going to use conservation of linear momentum in order to solve this guy. Now, they also tell us that the collision is elastic, okay? So maybe we're going to have to combine this along with our relative velocity statement that we did on the previous case. All right, so let's start off by writing down momentum conservation. So this is what we would have. Initially, all we have is m1, v1 initial. And after, what do we have? We're going to have m1, v1 final, plus m2, v2 final. All right, that is equation 1. Now, the relative velocities tell us this. So if I go v1 initial, mine is 0 because the initial one's not moving, has to be equal to minus v1 final minus v2 final. All right, this is our second equation. What I'm looking for is to solve for v2 final. Okay, so the easiest way to do that is you have two equations and two unknowns. What I'm going to do is I'm going to try to eliminate this v1 final. The easiest way I can do that is by multiply by m1 on both sides. Okay, and now if I add equations 1 and 2, I'm going to get a new equation that's going to eliminate V1 final. Okay, so look at what happens. If you add equations 1 and 2, the left-hand side, you end up getting 2m1 v1. That's my initial velocity, right? Okay, of object 1. And look at on this side, when I add 1 and 2, the v1 final terms cancel out, but look at the bottom terms. They're actually going to add together, okay? So this is actually going to be m2 v2 final plus m1 v2 final. You factor out the v2 final, and this is what you end up getting. m1 v1 final, v1 initial rather, divided by the total mass. Again, this is just one way to isolate v2 final. You can do isolation and substitution. That works fine. So now we have to substitute in all their numbers. So we get 2. The mass of m1 is also 2. It was initially moving at 3.1 meters per second. And now I divide by the total mass. This is 2 plus 3. So my v2 final for this problem is 2.48 meters per second. Now you really had to set up 2 equations and 2 unknowns for this problem in order to solve for v2 final. The correct answer for this one is E. All right, if the collision is elastic, what is the speed of cart number 2 relative to cart number 1 after the collision? Again, for this, we're going to use our relative velocity. So if I do v2 final minus v1 final, that is what they're asking me for. Okay, but if it's elastic, I can do this. It's v2 initial minus v1 initial. Very easy to do this. The relative velocity after is equal to minus the relative velocity before, if it's an elastic collision. And I know everything here on the left-hand side. So I have minus the initial velocity of object 2 was 0. And then minus what is the initial velocity of object 1? That was 3.1. So at the end here, we're going to get a positive 3.1 meters per second. Okay, that there corresponds to choice B. All right, question 19 says, instead of colliding elastically, suppose the carts now stick together. In that case, what is the speed of the 2 carts after the collision? Here we use conservation of linear momentum. Before the collision, I have only m1 that's moving, and if they stick together, that means the total mass after is m1 plus m2, and everything is sliding together at the same common final speed. Go ahead now and solve this. This is m1 v1 divided by m1 plus m2. Substituting our numbers, we get 3.1 divided by 2 plus, that should be 3 kilograms. Oh my goodness, what happened here? This here should be 1.24 meters per second. Now in the calculator up above, I actually did substitute 3 inside the calculator, but I wrote 5 for some reason. I'm not sure what happened there, but the correct answer is still 2.48 for that problem, and the correct answer for this one is 1.24. All right, let's go to problem 11 now. All right, problem 11 says, on a billiard table, a white ball strikes a red ball that's initially at rest before the collision. After the collision, both balls are observed to move along the same line. The speed of the white ball before the collision is 2 meters per second, and after the collision, it's 0.3 meters per second. The speed of the red ball after the collision is 1.7. All right, the white and red balls have the same mass. For this set of questions, assume the billiard balls are sliding on a frictionless surface. All right, first question, they want to know if the collision is elastic, completely inelastic, or elastic. All right, so how do we do this? Well, to check whether it's inelastic or elastic, we can look at our relative velocities before and after the collision. Okay, before the collision, we have everything we need, right? Because we know the white ball is moving like this. But after the collision, we only have, we actually have both right now. So we're ready to go. So let's go see what the relative velocity is before the collision, and then look at after the collision. Okay, so before, what I would do would be, well, let's say the velocity of the white before minus the velocity of the red before. Okay, so what do we have? Before we have 2 minus 0 gives me positive 2 meters per second. All right, now we can look at the relative velocity after the collision. Okay, so after, what we're going to have is the velocity of the white after, and then minus the velocity of the red after. Now, if you really wanted to write an equation, you can do like this. The relative velocity before is minus the relative velocity after. All right, so what do we have after the collision for the white ball? The white ball is moving at 0.3. Okay, so this we put 0.3. I put positive 0.3. Oh, actually, they don't tell me the direction. Oh, so I better be a little bit careful here. So we better determine which direction is this white ball moving. They don't tell us. All right, so for that, what I have to use now is conservation of linear momentum. So this is what we have. We have that the mass of the white one before the collision multiplied by the velocity of the white before the collision must be equal to the mass velocity of the white after the collision, and then plus the mass and velocity of the red after the collision. Now the masses are all the same, which is kind of nice. This simplifies everything, and it will allow you to determine this. So what is the velocity of the white ball after the collision? It's the velocity of the white ball before the collision minus the velocity of the red ball after the collision. All right, so the white ball before was positive 2, and the red ball after the collision here is 1.7. All right, so in that one we know it's positive 1.7 because it's moving here to the right. So look what we get. We get positive 0.3 meters per second, and the positive sign means it's moving to the right. All right, so this is important. Now you can go back to my other problem. So here I would have minus, and here I have 0.3. And then minus, what is the red after the collision? It is 1.7. All right, so we get positive 1.4. The fact that both of these numbers are not the exact same tells me right away that it's an inelastic collision. In what direction is the white ball moving after the collision? Well, this is what we just determined right here, right? It has to be moving in the positive direction using momentum conservation. Let me just write that down, conservation. All right, a little bit of a tricky problem. Again, we didn't know what the white one was doing. We only knew that the speed was 0.3, but we didn't really know its direction. All right, let's go to problem 12 now. All right, here's problem 12. We have two blocks of mass M1 and M2 are moving toward each other along a narrow, stationary, frictionless track. Block 1 is initially moving to the right with a speed of 3 meters per second. Block 2 is moving to the left with an initial speed of 2 meters per second relative to the track. After the collision, the masses move along the track. All right. First problem says, what is the direction of the momentum of the system of the two blocks before the collision? All right, so this is what we can look at. Well, we can write before. We can look at the momentum of each one, right? So the first one is M1 V1. It has a magnitude of 6, right? Kilograms meters per second, and its direction is that way. P2 is M2 V2. Okay, so the mass is 5 multiplied by its speed is 2. That gives me 10 kilograms meters per second. The direction of that vector, however, has to be in this direction. So if you add them up as vectors, we know that P2 is bigger than P1, so the total then should be also to the left. All right, so that's pretty simple. You just got to remember that we have direction associated with each of those values. All right, if after the collision block 1 is moving to the left with a speed of 0.5 meters per second, what is the speed of block 2 after the collision? For this one, we are going to use conservation of linear momentum. So we have what? M1 V1 initial plus M2 V2 initial must be equal to M1 V1 final plus M2 V2 final. We are looking to solve for what is this. Okay, so before the collision, we have exactly what we need. We have this guy is plus 6, and this guy here is minus 10, taking the direction into consideration. After the collision, we have 2 here, and its velocity is moving to the left. So I put minus 0.5 for its velocity, plus M2, which was 5, multiplied by its final velocity. So what you have to do now is simply solve for V2 final. All right, so I do a little bit of algebra here. V2 final is going to be, this is minus 4. I bring this onto the other side. That becomes positive 1. And then I have to divide by that total mass. So I should get like minus 3 over 5, which gives me minus 0.6 meters per second. Now they are asking me for the speed, so you're only going to have positive values here. We're just looking for the magnitude of that one, but clearly this here has to be the correct answer. All right, next problem says the experiment is repeated, but magnets are attached to the block, so they stick and they slide together after the collision. What's the speed of the two-block system? This is, again, a conservation of linear momentum problem. All right, now they stick together, so that means everything is stuck together. We have one final chunk of stuff, and it's moving at some final speed. All right, so just have to solve for what is this V final. So we have that initial momentum plus m2v2 divided by the total mass of our system. All right, we substitute in all our values here. We have 6 minus 10 that we did before. That's the initial momentum of the problem. And the total mass now is 2 plus 5, which is 7 kg. So you're going to get minus 4 over 7. Plug that in the calculator, you get minus 0.571 meters per second. Again, they are asking you for the speed, so really it is just the magnitude of that term, 0.571 meters per second. That there corresponds to choice C is the correct answer. All right, last problem is a conceptual one. The experiment is repeated but with a small explosive attached to the blocks, such that after the collision, both blocks are moving faster than they were before the collision. Which of the following statements is true? Well, if they're moving faster than they were before the collision, if they're going to be moving faster, clearly kinetic energy is not going to be the same. Okay, so kinetic energy of the two blocks is definitely going to be larger after the collision. So that one is definitely true. Let's look at the other ones. Both momentum and kinetic energy of the two blocks are larger. The momentum of the two-block system is larger after the collision. All right, so again, even though you have this explosive here between the two blocks, it's still a force that is internal to the two blocks. Okay, so momentum is still going to be conserved, so therefore momentum is not going to change before and after. All right, that's it for this problem. Let's go to 13. All right, problem 13 says this: a cart M1 with a mass of 0.6 is moving to the right on a frictionless linear track with an initial speed of 1.2 meters per second. It undergoes an elastic collision with a cart of mass M2, 0.25 moving to the left with a speed of this. All right, what is the velocity? The x component of the velocity of the center of mass of the two-cart system. So this is really just applying our definition. What is the velocity of the center of mass? You divide by the total mass of the system, which is m1 plus m2, and then you have to evaluate this sum here. It's the mass of each object multiplied by its velocity. Okay, so for this one, this is what it looks like. We have 0.6, that's the mass of m1. Its velocity here was 1.2, plus the second block, 0.25, is its mass. Now its velocity is 1.8 to the left. So in that case, I have to do minus 1.8 and then divide here by the total mass of the system, 0.6 plus 0.25. Substitute all those numbers in the calculator, you get a velocity of the center of mass, which is 0.32 meters per second. All right, go ahead and box that up. Okay, great. Next problem says, what is a V1 final, the velocity of cart number 1 after the collision? Okay, so this is a little bit of a more difficult problem because you're not told anything about what's going on after the collision. So it's really two equations and two unknowns. So I'm going to write down our two equations. This is what we have. Before the collision, we have m1 v1 initial plus m2 v2 initial, okay, must be equal to m1 v1 final plus m2 v2 final. Okay, that is one equation. That is linear momentum conservation. If they told us now that it's an elastic collision, you could write down conservation of kinetic energy. m1 v1 initial squared plus 1/2 m2 v2 initial squared equals to 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. Okay, so you have two equations and two unknowns. The unknowns are v1 final and v2 final. Now this one, although it is correct, it is more difficult to deal with because of all of these squared terms. So what I would do is, instead of using this, all right, I've shown this in one of my previous videos, but if it's a 1D elastic collision, this second equation here reduces to something that is much easier, which looks like this: v1 initial minus v2 initial, that's the relative velocity before the collision, must be equal to the relative velocity after the collision, minus v2 final. So this is my new equation for conservation of kinetic energy. Now you still have a bit of work because we really wanted to solve what is v2 final, or sorry, v1 final in this case. That's what we are trying to solve, right? Just this guy. But it appears in both equations, which means we need to eliminate v2 final. So I'm going to leave you do the algebra here. You can do isolation and substitution, but this is what the final expression should be. That v1 final, all right, if you be careful with the math, it should look like this: m1 minus m2 divided by m1 plus m2, all of this multiplied by v1 initial. And then you have another term here which looks like this: it's 2m2 divided by m1 plus m2 multiplied by 2 initial. So I have the final speed, or final velocity rather, it's written in terms of all of these initial quantities. And now I can substitute in all the values. So let's go ahead and do that. So this is 0.6 minus 0.25 divided by 0.6 plus 0.25. The initial velocity of cart number 1 was positive 1.2 plus 2 times 0.25. Again, divided by this same total mass, 0.6 plus 0.25. Multiply this by the initial velocity in the for cart number 2. Now that velocity, you got to be careful. This guy here is minus 1.8. So you do this, all of this work, and it is quite a bit of work, and you should get that the final velocity is minus 0.56 meters per second. Not an easy problem, okay? But these are the steps in order to solve this one. So that there corresponds to choice D. All right, let's go to problem 14 now. All right, here's problem 14. Prior to colliding, two blocks with mass m1, 1.5, and m2, 4.5, move toward each other on a horizontal frictionless track with a speed of 6 and 1.5. The collision is completely inelastic, and afterward the two blocks are joined together. After the collision, the two blocks move to the negative x direction, move to the positive x direction, are stationary. All right, well, you simply have to know that the initial momentum of the system before and after the collision is going to be the same, okay? So let's go ahead and write it down. We know everything before the collision, so we can figure this out. It'll tell us what's going on after the collision. Before the collision, we have object 1, which has linear momentum, plus object 2, which has linear momentum. And I'll just put an I here for initial, and this is what we have. M1 V1 initial plus M2 V2 initial. We substitute the numbers. We have 1.5. Here we have initial velocity is positive 6 plus M2. Here is 4.5. And its velocity is, now careful, minus 1.5 because they're going toward each other. That means that before the collision, if I substitute all of this, I get plus 2.25 kilograms meters per second. That's the initial momentum of the system. It's also equal to the final momentum of the system. The fact that this is positive tells me everything here is going to be moving to the right direction because that's the direction I've defined to be the positive direction. All right, so that means B is the correct answer for this one. Now this is a, what do they call it? A completely inelastic collision. So they want here to find, in question 2 here, the ratio of the total kinetic energy to the total final. Okay, so you want the initial to the final. All right. Well, now we can calculate it because we know everything. So what is this initial value? We just do 1/2. What else? M1 V1 initial plus 1/2 M2 V2 initial. And you have to square those. All right, so this you can calculate it. We're just going to substitute in all our numbers for the masses and those initial velocities. And if you do that, you should get like 32.1 joules. All right, so we need to also calculate what the final kinetic energy is, okay? Because we have to divide by this term. So this here is 1/2. The total mass now is m1 plus m2, but you need to find what is this final speed after the collision. And in order to do that, what you do is you do conservation of linear momentum. We're going to go up here. We know the total final momentum is 2.25. Well, this must be equal to the total mass, m1 plus m2, multiplied by that final speed. All right, so that final speed then is going to be our 2.25 divided by the total mass, which is 1.5 plus 4.5. Oh, plus 4.5. I say 5 and I write down 6. I don't know what is going on with my brain today. All right, now this gives me a final velocity here of positive 0.375 meters per second. So now it's easy to calculate what this denominator is here for my final kinetic energy. I actually get a really small number, 0.422. So you've lost so much energy here by having this completely inelastic collision. Substitute the numbers in that calculator, you should get roughly 76 for that ratio. So that there corresponds to choice A. All right, which of the following best describes V star, the velocity of the two blocks in the center of mass frame? All right, so what would we do this? Is V star is 0? Is it this? Or is it negative or positive? Okay, so how do we determine this? Well, the velocity of the two blocks, first of all, the velocity of the two blocks in the center of mass frame, the velocity of the center of mass, remember, does not change in a collision, okay? It cannot change. Okay, that is really another way of writing down conservation of linear momentum, okay? So think about it after you have everything here moving at some V final that we calculated. Well, clearly the center of mass is also moving this way at the same V final, right? So relative to the center of mass, the velocity of the two blocks has to be 0, and it's the same before and after the collision, okay? So this one here is A is the correct answer. So you just have to know something about the center of mass velocity and how it applies in collisions. All right, here's problem 15. It says a steel ball of mass m is attached to the end of a massless string of length 0.75 meters, which is fixed at the opposite end. The string is pulled taut and held horizontally as shown above. The ball is then released from rest. At the bottom of the path, the ball strikes a steel block which has a mass of 3m. It's initially at rest on a horizontal frictionless surface. First problem says, what is the speed of the ball just before the collision? So we want to know when the ball kind of swings down over here, just before it strikes this one, what is its speed? For that one, we use conservation of energy, okay? So down over here at the bottom, it's going to have a lot of kinetic energy, okay? But at the start, it had a lot of gravitational potential energy. So you simply have to set those to each other. There's no energy loss here in that swinging motion. So this is what it looks like. So at the end, we have 1/2 m v squared. And this is really going to be the initial velocity of that one, okay, before the collision. And this here has to be equal to the potential energy, which is mg times the height. Well, what is the height? The height is simply going to be the length of that string. Okay, so the masses cancel out on both sides. We're simply solving for that velocity here. Again, I've called it V initial because it's going to be the initial right before the collision. So what do you get? Square root of 2GL. Substitute in our numbers here, 2, 9.8. And my length here was 0.75. Okay, we get that velocity, which gave me 3.8 meters per second. All right, that there corresponds to choice B as the correct answer. All right, next problem says, let V represent the velocity of the ball just before the collision. Okay, that's what we just calculated. If the velocity of the ball just after the collision is minus V over 3, what is the velocity of the block after the collision? For this, we will use conservation of linear momentum. So what do we have? We have m moving at some velocity v that I just calculated, vi, okay? And this has to be equal to, well, after the collision, we have that ball bounce back. So we have a minus m v over 3. The negative sign tells me that it's moving to the left, okay? And now what? Plus the mass of the big block is 3m, and I'm trying to find its final velocity over here. So that's the only unknown in this problem. Again, you could start off maybe by crossing out some of those mass terms, bring that on the other side. What you end up getting here is 4/3 times that initial velocity, okay? And that has to be 3 times Vf. So we get Vf is 4/9, which is 4/9 times, that initial velocity. I can't forget that term. All right, so you look at the choices now. All the choices are in terms of that initial velocity. That looks a lot like choice D to me. All right, next problem says, what can you tell about the character of this collision? Look at the first choice. The collision was completely elastic, the collision was inelastic, or there's not enough information. So like we've done many times now, you can look at the relative velocity before the collision, right? Before the collision, what is our relative velocity? We have V1 initial minus V2 initial. V2 initial was 0, so we simply have V initial. Okay, what do we have after the collision? After the collision, we have minus V1 final minus V2 final. All right, we substitute our numbers over here. So we get minus V1 final. Here we said it bounced back, right? So this was minus Vi over 3. And now V2 final minus 4/9. All right, Vi. All right, we substitute the numbers here, and what you're going to get here, so how many ninths is this? This is 3/9. That's 7/9. 7/9. Okay, Vi. Notice that these numbers are not the same, okay? If they're not the same, then you know it has to be an elastic collision. If they are the same, it is a completely elastic collision. So the best choice for this one is choice B. Problem 16, an object is at rest just before it explodes into 3 equally massive fragments. Right after the explosion, one of the fragments, M1, travels in the positive y direction with a velocity v1. The other 2 fragments travel at angles plus or minus theta with respect to that negative y-axis as shown in the figure down over here. We are also told in the figure here that the masses are all the same and that the speeds of fragment 2 and 3 are also the same. Okay, so I'm just going to call this V at the end. Okay, so what is K1 to K2? The ratio of the kinetic energy of fragment 1 to the kinetic energy of fragment 2. All right, so they involve all different choices. There's really no way of doing this without just calculating it. Okay, so this is what they're looking for, the ratio of K1 to K2. Now they're only looking at one of the fragments, okay, so let's just be careful here. So before, what do we have? We have m v1 squared, and then for one of those fragments, what do you have? 1/2 m v2 squared. Okay, so the 1/2 terms leave. The masses can cancel out, so we need to somehow determine this ratio. What we need to do now is try to determine how can we figure out this speed here after the collision, okay? For that, we have to use conservation of linear momentum. And I'm going to look at the momentum here in this vertical direction, in this y direction. All right, so what do we have before the collision? Before the collision, you have 0, okay? And then after the collision, what do we have? We have m moving up at some speed v1, okay? And what else? Now I have both of those fragments, right? And they're moving down, right? So I'm going to do 2. There's both of them. They both have momentum here in that vertical direction. Their velocities now in that vertical direction, again, if that's the angle theta, it should be negative, and it's going to be some final speed 2, and I need to only grab the component along the y-axis. So this here should be cosine of theta. All right, so this allows me to solve now. Again, the masses could cancel out because they appear on both sides. Let me get to this final expression that V2 is equal to V1 divided by 2 cosine of theta. Okay, so this is good because it allows me to substitute down over here in the denominator of my expression. So I have V1 squared divided by this entire term here is squared. This is V1 divided by 2 cosine of theta, and you have to square that whole term. Once you do all of that, the v1 terms are going to cancel out, and you're going to be left with 4 cosine squared of theta. Okay, and that there corresponds to choice E. Not an obvious one, but again, you have to use conservation of linear momentum for this one. Certainly not conservation of kinetic energy when you have an explosion like this. Next problem says, if the explosion resulted in particle 2 and particle 3 leaving at a larger angle, they ask, the center of mass after the explosion would move upward, the center of mass would move downward, or the center of mass would move at rest. The velocity of the center of mass before a collision or an explosion like this must be equal to the velocity of the center of mass after. Okay, there is no change in the velocity of the center of mass, and that's a really important property of collisions. So that means that if it was initially at rest before the explosion, it must be also at rest after the explosion. This is the same expression as conservation of linear momentum. Okay, it is identical. So identical to conservation of linear momentum. Let me just write that down. All right, so that's it for this problem. Let's go to 17. Here's problem 17. It says a person with mass of 80 kilograms is standing still on frictionless horizontal ice and then throws a 0.25 kilogram ball in the horizontal direction. After throwing the ball, the person is observed to be sliding backward with a speed of 0.04 meters per second with respect to the ice. What is the speed v ball, the horizontal component of the speed of the ball with respect to the ice? All right, so before there is nothing going on, right? This is all we have before. They got the guy holding the ball, and then after, well, the ball is moving this way, and then that means that the man has to move this way. Okay, so before we have zero momentum, and then after we have the man and the velocity of the man. This must be equal to the mass of the ball and the velocity of the ball. So what we're looking for here is the velocity of the ball after the collision, after the throw rather. So you bring that term on the other side, so you get minus mv of the man divided by little mass of the ball. The speed of the ball now, again, the negative sign is going to indicate to us the direction, but now we just substitute our numbers. So we have the masses, 80 divided by 0.25, and then that velocity of the man is moving backwards, so it's 0.04. I put a negative sign just to tell me the direction. And the ball now is going to be moving at roughly 12.8 meters per second. Just round that to 13, and it gives you choice C right here. All right, what else do we know? What is the magnitude of the average horizontal force by the hand on the ball, assuming it took 0.5 seconds to accelerate the ball? So our average force here, you can write it as the change of momentum of the ball, right, over the change in time, okay? What is the change of momentum of the ball? Well, it's P final of the ball. It's the mass of the ball times its V final, okay? It was initially not moving, so that's it, minus 0, divided by that time, which is 0.15 seconds. All right, so we can go ahead and substitute here. We get 0.25 is that mass. The speed of the ball we just calculated as 12.8. All right, divided by 0.15. That gives us an average force of approximately 21.3 newtons. Okay, so the correct answer for this one is choice C. All right, pretty straightforward problem. Let's go to the last problem, problem 18. Here's our last problem. We have a block of mass m1 slides on a horizontal frictionless surface with a velocity v1. It collides with an ideal massless spring, which is attached to a block of mass m2, which is initially at rest. The spring has a spring constant of k equals to 175. First problem says, what is the common speed vc of the two masses will be moving when the spring is at the maximum compression? Okay, so that's kind of a key word over here. And one thing to just think about here is that at the maximum compression, both blocks have to be moving at the same common speed. Okay, so v1 must be equal to v2 must be equal to that common speed. All right, so they want us to find what this common speed is. What you do here is we use conservation of linear momentum. Before, all we have is m1, and it's moving at some velocity v1. At the maximum compression, everything's moving together. Therefore, you have M1 plus M2 multiplied by VC. So we now have an expression for VC. Divide through by that total mass, and you can see that that corresponds to choice C. The last problem here says if they give us the masses, so M1 is 1.5, M2 is 6, and the common velocity, they give us VC now, okay, that's this guy. What is the maximum compression of that spring? All right, for this one, what we're going to use now, since this is a spring, it's an ideal spring, we're going to use the concept of conservation of total mechanical energy. All right, so before the block hits the spring, the total energy of our system is K initial. Okay. And then at the maximum compression, what do you have? You have everything that's moving, therefore it has some final kinetic energy, but now the spring has some potential energy stored into that system because I've compressed it a certain amount. And I'm trying to find what is that compression. So let's write down what is our initial kinetic energy. It's 1/2 M1 V1 squared. Now, nowhere have I told you what V1 is, right? We still don't know this, but we could probably determine it from this expression over here. All right, what else do we know? Well, we know that at the maximum compression, my kinetic energy is M1 plus M2, and everything is moving together at that V common squared, or V common, and then I have to square that to get the kinetic energy. At the maximum compression now, I also have some spring potential energy. It's 1/2 multiplied by the spring constant, multiplied by that maximum compression, and I square that term. All right, so I'm going to start off here. Let's just by canceling this out. I need to find V1 initial, and once I do that, my only unknown is going to be this maximum compression. So to find V1, I'm going to go back to this expression, and I'm going to do this. M1 plus M2, just isolate it, divided by M1 multiplied by VC. So V1, I could get a number for this because the masses here are 1.5 plus 6 divided by 1.5. Okay. And now what? I need to multiply by that V common, which they told me in this question is 0.4. So this here actually gives me 2 meters per second. All right, so I really know what this guy is now. I don't have to, let's get rid of that. We know what this initial velocity is. So now let's just get my final expression for that maximum compression. This is what it should look like. That the X max, be careful with the algebra here. So we have M1 V1 squared. I have to bring this entire term here to the other side. Minus M1 plus M2 V common squared. I have to divide all of this by the spring constant K. And now I have to take a square root. Okay, now I could substitute in all our numbers. All right, last step. Let's get this correct here. We have 1.5. I have 2 squared minus 1.5 plus 6. That's the total mass. The common is 0.4 squared. And now my spring constant is 175. That's already in the proper units. All right, if I take care of all this, I should get 0.166 meters. That is the maximum compression of that spring. And this concludes this monster problem set dealing with momentum and collisions. All right, so the correct answer for this one is C. All right, folks, that's it for me. We'll see you next time.